Hello, in this video we are going to be factorizing polynomials. I wrote here for you to remember the factor theorem. If we have a polynomial function p and a real number c, then we know that c is a zero of the polynomial function if and only if x minus c is a factor of p. We are going to be using this theorem in a few examples. We are going to also keep in mind the fundamental theorem of algebra that says that in the real numbers, if we have a polynomial with degree n, then we can have up to n zeros for it. In our first example, we want to fully factorize a polynomial function of degree 4, knowing that 2 and 3 are zeros of this function. So what we know then is that when we manage finally to write the factorization, we are going to have a factor that has x minus 2, a factor that has x minus 3, and then we are going to have another polynomial. Let me call this polynomial function q of x, and this is going to have degree 2. So we want to find what that polynomial function q of x is, and we also want to try to factorize it, because a polynomial of degree 2, we could be able to factorize it in the real numbers. Could be that we can't, but we have to check in which case we are. So we could divide our polynomial by the factors that we already know, so by x minus 2 and x minus 3. We could do long division, or we can instead apply synthetic substitution. So what we are going to do in this case is write the coefficient 2, -7, -2, 13, and 6, and we're going to use synthetic substitution to divide by x minus 2, so we are going to use synthetic substitution for the value 2. So I hope you remember how to do this. We have 2 times 2, that's 4, -7 plus 4, that's -3. Again, we multiply the -3 by 2, that's -6. Now we sum -2 and -6 to get -8. Multiply by 2, -16. 13 plus -16, that's -3. -3 times 2, that's -6. When we sum 6 and -6, we get 0. Okay, so far we are doing good. We got that the remainder is 0, so that means that, yeah, x minus 2 is really a factor of the polynomial, as they told us. But even more important, we got here these numbers 2, -3, -8, -3, that are the coefficients of the polynomial we obtain as a quotient if we divide p of x by the linear factor x minus 2. So what I'm saying over here is that our polynomial p of x can be written as x minus 2 times 2x cubed, the 2 is coming here, minus 3x squared, here is the minus 3 coming from, minus 8x minus 3. And there is no remainder. Well, technically we need to write plus 0 here for the remainder. So now we have a polynomial function of degree 3 that we would like to factorize, and we know that 3 has to be a zero of it, so it has to have a factor of x minus 3. So we're going to apply synthetic substitution again. So now our new polynomial has coefficients 2, -3, -8, and -3, and we are dividing by 3. Well, we're dividing by x minus 3, so we need to write just 3 here. If I didn't write all this factorization I wrote over here, I could have continued going down from here, but okay, well, we don't have space, so let's do it here on the side. So again, I'm doing this quickly, but you can just pause, do it in your notes, and then catch up with me. 6, 3, 9, 1, 3, 0. So once again, we know we are doing fine because we got a remainder of 0. So far we know that our polynomial function can be written as x minus 2 times x minus 3 times, and now this is the q of x polynomial we're talking about, 2x squared plus 3x plus 1. Now that's what we have to check whether we can factorize or not. Let's see. I think we can try to just kind of mix guessing and split in the middle term. There's going to be 2x, then something, then x, something. We need both of the signs to be positive, and we need the product to be 1. So let me check that this is enough. 2x squared plus 2x plus x plus 1. Yeah, that's correct. So we fully factorize the polynomial function given. For our second example, we are trying to fully factorize a polynomial function of degree 3. So we have x cubed minus 5x squared minus x plus 5. Okay, looks like we are in trouble because we don't have any method to factorize polynomials of degree 3, and we're not giving any zero of the polynomial function. So what do we do? Well, in this case, we're just going to have to try to guess what a root could be for this polynomial. Something you could notice is that if you look at the coefficients, we have 1, negative 5, negative 1, and 5. The sum of the coefficients is 0. 1 and 5 are the positive ones, negative 5, negative 1, the negative ones, so they cancel out. So that means that if we evaluate our function at 1, so t at 1, this is the result we get, which is 0. So what we are saying is that by looking at the coefficients, we can guess that 1 is a 0 of the polynomial function, and then we know that x minus 1 is a factor. And if we find a factor, we are good to go, because then we will be left with a polynomial function of degree 2 that we can, of course, try to factorize. Okay, we were lucky here. What if 1 is not a 0 of the polynomial function? Well, then I would say try with negative 1 and with 2 and with negative 2. If you're not given more information and you're just supposed to guess, then the guess cannot be that hard. So now that we know that x minus 1 is a factor, let's divide our polynomial by x minus 1 by applying synthetic substitution. So we have 1, negative 5, negative 1, and 5 for the coefficients, and we're substituting by 1. So we are going to be left with, I'll do this quickly, you can do it yourself, negative 5, 0. So we check again, the result was what we wanted. So the polynomial we are left with, let's call it q of x, is x squared minus 4x minus 5. And we like to factorize this polynomial if it's possible to factorize it. We can check quickly if that's possible or not. Well, we can find the discriminant, so we'll have negative 4 squared minus 4 times 1 times negative 5. So this is going to be positive. This is 16 plus 20, which is 36. Not only is positive, but it's a perfect square. So we're going to be able to factorize this in the rational number. So let's see if we can just look at the sum and the products of the roots. We're going to have x times x something else. One of the signs has to be negative, but the other one has to be positive by looking at the signs of the coefficients. And the product has to be 5, and the sum has to be, negative 5, and the sum has to be negative 4. So I'll write negative 5 plus 1, yeah? X squared plus x minus 5x minus 5. So what we have showed is that full factorization of our polynomial function is x minus 1 times x plus 1 times x minus 5. For our last example, we are going to find two values, a and b, knowing that those are coefficients of a polynomial function of degree 4 given here, 2x4 minus 5x3 minus 14x squared plus ax plus b equals f of x, knowing that both 1 and 4 are zeros of the polynomial function. So we're going to, one more time, begin by applying syntactic substitution. We do know that 1 and 4 are zeros, so if we apply syntactic substitution, we'll get remainder of 0. So let's do it. We start with the coefficients 2, negative 5, negative 14, a, b, and let's start with the number 1. So 2 times 1, and again, I'll do this quickly. You can do it yourself. So the remainder will be a plus b minus 17. But since 1 is a 0, this has to be 0. We can go ahead and substitute also by 4. We have the coefficients we need left already over here. So let's do it. 5 to 10. And again, the remainder has to be 0. So what we are saying is that a minus 5 had to be 0. So we found that the value of a has to be 5. Now we can go ahead and use the other equation to find the value of b. So 5 plus b minus 17 has to be 0. So b is equal to 12. So those were the two values we were required to find.